Hey everyone, and a very happy Tuesday. Welcome to Tech Talk Tuesday with today's ARM Tech Talk series. This is the place for the latest and greatest in trends, technologies, and best practices from ARM and our ecosystem partners. A particular warm welcome if this is your first Tech Talk, and for those of you joining again, well, it's great to have you back, whether joining on Zoom or on YouTube. Today we've got an awesome Tech Talk from our ecosystem partner Neuton.ai, talking about a smart toothbrush solution. And we've also got a little appearance as well at the end from our partner Infineon. So really excited to have them today. It's going to have a great demo. There's going to be a lot of really great technical insights that you're going to get in today's talk. So I just want to quickly cover, before we actually get into the meat of today's content and the presentation today, just want to cover a couple of quick topics around kind of how you can ask questions and what's coming up. So Blair, if you can go to the next slide, please, that would be awesome. So if you want to get involved in today's conversation, not only can you ask a question in the Q&A box in the Zoom menu bar, and please do that as the talk goes on. I'm sure there'll be tons of questions for Blair, Roman, Vivek, and the team. You can also tweet us using the hashtag ArmTechTalks and also post on LinkedIn using that hashtag too. All of our past Tech Talks are available on demand. There's an ARM Tech Talk playlist at youtube.com/ARM. Just look at the playlist. And you can sign up for all our upcoming talks at arm.com/Tech Talks. Speaking of what's coming up, let's have a look at the next slide as to the upcoming schedule. We're about to release the schedule for June, and we're just finalizing the title with our ecosystem partner, Sonatus, for our talk on May 30th. So we have today's presentation on the smart toothbrush with Neuton.ai, which is really exciting. Next week, we've got automotive. And in fact, the next 2 weeks, we've got quite a heavy automotive theme. So if you're interested in the latest automotive trends, technologies, and best practices, then make sure you sign up for those two talks. The Kern Concept one's already live. Sonatus will go live tomorrow. So keep an eye on our landing page for that because spaces are limited. So it's great you could actually make it to today's one because you're one of the lucky few who can get on the Zoom webinar. And then there'll be a whole host of talks coming up through June and into the early part of July too. But let's talk about today. Today, I'm thrilled to be joined by Blair Newman, Roman Rusak, and Vivek Shankar Kannan from Blair and Roman from Neuton, sorry, and Vivek from Infineon. And they'll be talking about the next generation smart toothbrush. As a matter of fact, you might recognize Blair because he's already made an appearance in today's Tech Talk. He actually made an appearance in that promo video. If you were eagle-eyed and spotted him, if not, just go back and rewatch. He was there as one of the highlighted speakers. So it's great to have Blair back today, and thrilled to have Roman and Vivek joining us as well as newcomers. So that's enough from me. I'm really looking forward to today's presentation content, as I'm sure you are too. So Blair, why don't you introduce yourself and our panel today and take it away with today's content. It's great you could join us. Thank you so much.
All right, thanks, Tobias. Definitely appreciate the introduction as well as the brief cameo on the introductory video. I appreciate that. It's always a pleasure to have an opportunity not only to work with ARM, but also to work with yourself. And by way of introduction, for those who have not had the opportunity to meet or interact with, my name is Blair Newman. I am the CTO here at Neuton.ai. I've had the opportunity to be at the organization from some time since its inception, as we've kind of embarked on this particular journey, really with, I would say, our mission has always been to enable everyone in a very literal sense to be able to grow this particular ecosystem when we talk about tinyML. And when it comes to Neuton, I believe that we have really taken the bull by its horns and really enabled and empowered everyone to continue to grow this particular community. And I believe that what we have lined up today, I believe that everyone will certainly enjoy, especially when it comes to a tech talk. One of the things that we wanted to do is to bring tinyML, EdgeML to life. And so not only will we be able to share with you guys one of the solutions that we've put together, but we'll also be able to demo live not only the solution in action, but also how you guys can have the opportunity to implement the solution yourselves moving forward. So joining me, I have the pleasure of having not only Roman, who is one of our principal research and embedded engineers who will take you guys through the solution today, Roman is been in this particular arena for a little over 7 years. He has an extensive amount of experience. And I won't go through all of the gory details, but I'll just say that he's certainly the individual that if you have any questions, any concerns in this particular area, he's certainly the one that you want to ask questions. We have a really jam-packed session. So next joining me will also be Vivek. Certainly very thankful for Infineon, who Vivek is the product marketing manager at Infineon. Certainly glad that he will be joining us today since we have the opportunity to demo our solution running on their particular platform as well. But let's kind of move forward and kind of begin to kind of get into the meat and potatoes of today's discussion. I'll start off just kind of give you a quick agenda. I'll share a little bit about our organization, what we're doing, if you haven't had the opportunity to be introduced to what we're doing in this particular space. Then we'll go, as I mentioned, into some details as it relates to what we're doing in the AI ML space, specifically around consumer electronics and a smart toothbrush. We'll give you guys an overview of this particular solution. Then we'll give you a demo as it relates to showing and demonstrating this particular solution in action. And then we'll kind of break down what are the hardware that we're using, the steps that you need to take in order to implement a similar solution. And so we'll also begin to wrap up with a practical solution as to, a practical session as it relates to collecting the necessary data, the necessary features, training your model, and then of course, deploying the model directly onto the device, and then obviously running inference on a particular device and seeing it in action real time. And then we'll have some time for questions at the end. So just once again, by way of introduction, one of the things that I mentioned earlier in my kind of brief intro is that we're really kind of focused on enabling everyone to be able to produce models that can run efficiently on the edge. One of the things that we're extremely proud of is that we consistently are able to produce models that what we tend to find are up to 10 times, sometimes even more smaller than what you might find with some of the other traditional algorithms and frameworks that are out there. So even though we take a completely different approach as it relates to building our particular solutions, so we don't leverage TensorFlow or any of those other algorithms that are out there. This is an algorithm that we've developed in-house. Even though it's our own, I would say, patented and unique framework, all of the models that we're producing are 100% open, and more importantly, they're device agnostic. We have the ability to embed our models natively after one iteration into 8-bit, 16-bit, 32-bit MCUs, and of course, even directly on a sensor, if that's something that you're looking to accomplish as well. And one of the other things that we're extremely proud of is that we eliminate the need for you to provide or for you to perform any compression techniques. So you don't have to do pruning, quantization, or anything like that. So in one iteration, our platform is going to produce a model that is natively compact right out of the box and really empower and enable you to embed that particular model into any device of your particular choosing. So once again, really kind of focused on enabling everyone in our community to be able to move forward and push tinyML very strongly as we move forward. So some of the areas that we're pretty active in, whether it's predictive maintenance, whether it's human activity recognition, asset tracking, et cetera. Here we'll be demoing or sharing with you guys something that we're doing from a human activity recognition perspective, specifically as it relates to personal health care. Now, as we all know, when it comes to tinyML, EdgeML, it's the constant challenge of being able to produce a model, embed that particular model into your particular device and not consume all of the respective battery life that you have. As we know, when it comes to Edge, tinyML, battery life is your currency, space is your currency. And these are the two areas that we're extremely proud of, that we're able to produce models oftentimes less than a kilobyte in size, the entire solution less than 5 kilobytes in size, so that you can really leverage your particular real estate on your application and not on the model itself. So we're extremely proud that we're able to produce models that enable all of you guys to bring intelligence to the edge without sacrificing your energy consumption, without sacrificing the real estate as it relates to space, especially when it comes to being able to produce something in the field and you want to prolong the particular life of the solution that you're implementing. So enough of me. I'll move forward. I will move forward, and I will introduce Roman. Roman, as I mentioned, he's one of the most experienced guys when it comes to the embedded world as it relates to producing these solutions. So I'd like to take a moment to introduce him, and he'll take it from here. And I'm sure you guys will extremely enjoy the solution that he has coming up. All right, Roman, I'll hand it over to you, and you should be able to control my screen.
Thank you, Blair. Yes, and today I think our main focus will be on the application of AI and ML in consumer electronics. And the application of ML in consumer electronics has changed the way we interact with devices, creating smarter, more personalized and efficient experience, from voice assistants, smart assistants, to gesture control interfaces. And all these technologies have reshaped the consumer electronics industry. And as AI and ML continue to advance, we think that we can expect even more innovative application, driving further enhancement in functionality, convenience, and sustainability. And in our opinion, the future of consumer electronics lies in the seamless integration of ML, delivering products that are intelligent, adaptive, and capable of enriching our lives in a way we never imagined before. And let's look at some examples. In the wearable industry, we have smart rings that employ AI algorithms to interpret gestures of wearer and may include stress monitoring feature by analyzing heart rate variability. Some smart wearables incorporate AI algorithms to detect false or unusual movements, also algorithms to analyze the ECG data to detect irregular heart rate, such as arterial fibrillation. Also, we see more and more examples in smart home appliance. And one of them, smart washing machines that can accurately determine the weight and a type of laundry and optimize energy and water consumption. Another example is vacuum robots that can detect type of floor based on level of softness, and if the robot vacuum cleaner detects soft materials like carpet, it changes the cleaning mode to avoid using water on this type of surface. Another great examples in the smart personal care products is the smart toothbrushes. And AI-enabled toothbrushes incorporate sensors and machine learning algorithms to analyze brushing techniques, duration, and pressure. Also, we saw the appearance of AI-powered smart scales that can utilize AI capabilities for analyzing body composition, track weight, trends, provide insight of overall health and fitness. And last but not least, I think it's a hearable industry. And in hearables, there are a lot of tinyML examples, and one of them is gesture-based controls. And hearables with gesture detection capabilities allow users to control various functions or features through hand movements. And some of the hearables also has built-in accelerometer and AI algorithms that can detect fail detection. We see today more and more AI-enhanced product appears in consumer electronics, and in this session, we will talk and show one of such examples. Okay. Today we will talk about smart toothbrush, and we want to talk about this, not only about the technology, but how you can utilize this technology to benefit your business. And let's imagine you are a consumer electronic company and you want to start the smart toothbrush product or improve the current one. What goals do you want to achieve as a business for this product? What challenges do you want to solve? Of course, first of all, we need to provide real-time feedback about what area of the oral cavity user is brushing, right? Without it, our smart toothbrush will not be so smart after all. Also, we want to improve the user experience of our product. Not all users want to take their mobile phone to the bedroom to see real-time feedback. And based on these factors, we need to use ML algorithms or neural networks right on the device. But we know that such algorithms can sometimes be quite resource intensive, and we definitely do not want to put a supercomputer in our toothbrush. So our ML solutions should be resource and energy efficient, and this will allow us to reduce the hardware costs. Also, we need to consider R&D and support costs when we develop such product. The development of tinyML solution involves many expensive specialists in various fields: machine learning, signal processing, embedded software, and it's not always convenient to have such large team within a company. So we define these goals for our project. Provide the user feedback about which area of oral cavity he cleans in real time on the device, reduce battery consumption, reduce device hardware cost, provide the solutions should have low R&D cost, and also provide the solutions should have low maintenance and support cost. Okay, let's talk about what stages in the development of such embedded AI projects. First of all, we need to define the AI. Okay. Okay. First of all, we need to define AI use case for our product. What issue of our users we want to solve with AI? In our case, we want to provide real-time feedback so that users can take better care of their oral health. Okay, then we need to choose the target hardware, what sensor we will use, what microcontroller will manage all these. This is very important stage since it determines both the quality and the cost of your future device. After we have chosen the hardware and assembled our test device, we can proceed to the data collection stage. We will cover this stage in more detail in our practice session. Then we must properly prepare the data, clean it up, get rid of outliers and incorrect data that always take a place, label data. And after that, we're ready to create our ML solution. So the complexity of neural network will also depend on how correctly and efficiently we extract the features from the data. Even most powerful neural network will not be able to give you good results and with poor approach to feature extraction and selection. And development of the model architecture and its training can be both quite time-consuming stages or fast when you're using certain tools. In our practical session, we will show how we can speed up this process. So we have come up to the stage when we have trained our model and the idea, the concept of what features we need for inference. And now we need to understand how to put it all on the device. And if things are easier with NN model, even TensorFlow make it possible to use the neural network on microcontrollers. But with feature extraction and data pre-processing, everything is not so simple. And when you work with your Python code, you can use some libraries and extract hundreds of features use different filters, overlapping window, etc. in just one click. But then you should repeat all of this in C code, and this is not so easy. But doing it efficiently, even more difficult. So keep that in mind. And in our experience, tie everything together in the device firmware is the challenging part. And that's because we provide ready-to-use ML packages in a C code where everything included: data pre-processing, feature extraction, model inference, everything. And after this, we're ready for deployment to this model to device and validation. And in our experience, we see that the metric that it obtained on the holdout data set very often does not show how the model will work in real condition. So it is very important to have convenient tool for updating and retraining your model, polishing false positives, and editing new data. Oh, okay, it was a long journey. Let's move to a more interesting part. From theory to practice. First, we will show you how our smart toothbrush demo works. And then we discuss the results, how we achieved it. And so you can repeat this in your experiments. I will share my screen. Oh, first of all, I want to show our smart toothbrush. This is how it looks like. We have an IMU sensor and our wireless SoC on my hand. And now I will show you how it works on the real demo. I will connect the hardware to my PC, start everything up. And share my screen. Okay, I hope you can see my screen. I also stop my video to share a video from my PC to make it more convenient for you. Okay, at the left side of the screen, you can see our graphical user interface with, let's say, blueprint of the oral cavity. We divide the oral cavity into 9 zones. At the left gray box, you can see all 9 zones of the oral cavity and the percentage of cleanness. Also, at the top of the blueprint, you can see current device activity. Now my brush is idle, it's not moving. And if I started to move it, the activity will change to unknown because it's something that our model does not see. So let's start to brush some areas. I will start from front teeth, and let's imagine we have our morning routine. Okay, I will not cover all my areas to 100%. I don't want to waste our time, but let's finish some area to 100%, make it clean to 100%. Okay, now it's clean. And maybe continue with some another area, just last one, maybe upper left front. All right. So this is it. This is how it works. So we perfectly can recognize all 9 areas of our oral cavity. I can brush some areas that we did not cover in my session. For example, upper left back. All right. So yes, this is how it works. And right now we will talk about how we achieve this, what hardware we will use, and all other stuff regarding this solution. I will stop share my screen. Okay. All right. At the screen, you can see the technical specs of our solution. First of all, we have 11 classes, 9 areas of oral cavity, and 1 class for unknown random movements, and idle class when the toothbrush not moving at all. And let's remember what goals we set for ourselves developing this solution. To be able to provide real-time user feedback about brushing areas without a phone. We have 97% of accuracy in 11 classes, and you see how it works in real life. For the demo, of course, we demonstrate feedback with animation, but our tinyML solution works completely on the device level, and you can provide user feedback without a phone, for example, with the LED indication or with the help of haptic. And also it's worth to mention that even we show this demo on ordinary toothbrush, this will work well on the electrical toothbrush because we just need to recognize the orientation of the toothbrush and the type of movement, and the electrical toothbrush vibrate by themselves, and it gives us all needed information to recognize different areas of the oral cavity. We also want to make our product energy and cost efficient. And for our demo, we chose ARM Cortex-M architecture as it perfectly suits for battery-powered devices. Also, Cortex-M processors are typically more cost-effective compared to other architectures. And we test our solution on the Cortex-M4, 48 megahertz, and it shows great results in terms of energy efficiency and footprint. Our neural network is extremely small, as you can see, only 68 neurons. And with the Cortex-M instruction set, it makes the compiled code footprint even smaller. And as you can see, the total footprint of the entire solution, including data pre-processing, feature extraction, and model inference, so everything, is only 4.5 kilobytes of flash and 1.5 kilobytes of RAM. That's pretty amazing, actually. But what all these numbers mean for you as a product company, for example? This means so you don't need to buy expensive, powerful processors for your product. It also means that you will have much more resources left for your business logic and applications, wireless stacks, motor control, etc. And we have less than 2 milliseconds of inference time. Excuse me. And inference rate only 3 times per second. That includes feature extraction, that includes the data pre-processing. It means we have pretty low CPU usage, and the device could sleep more could sleep more time between inferences, and makes the device itself more battery efficient. And also, we need to we don't need to send the sensor data to the phone to make the real-time feedback. That also greatly enhance battery life and battery usage. So, in the summary, our tech advantages: real-time tracking at the edge. We don't need to use mobile application to provide the user feedback. Also, we don't need to send the sensor data, and we're reducing the battery consumption. And we don't need to store the sensor data because we analyze it in real time, and it greatly enhances hardware cost optimization. All right. Let's now talk about how we did it. Let's go back a little bit to the beginning. And in order to make our toothbrush intelligent, whether it's ordinary toothbrush or electrical toothbrush, we basically need three things. And IMU sensor to collect acceleration and orientation data of our toothbrush. Also, we need, let's say, AI brain to process the sensor data and provides meaningful results. And our Neuton does a great job with it. And last but not least, we need the wireless MCU for device management, to update the tinyML model on the device, collect new sensor data, connect with the mobile applications for providing user statistics, for example, in a month or in a week, etc. And for IMU sensor, for this project, we use Bosch BMI 116. DUE is energy efficiency and sensitivity that is crucial for our application, because we have very low amplitude movements and rotation of our toothbrush while we're brushing. Also, BMI 116 has a wide selection of output data rates that allow us to accurately find the output data rate we need for feature extraction. And it is important to note that this sensor has built-in digital filters that can help you clean data from noise for better feature extraction. Let's go to the wireless SoC that we use for this demo. And for our demo project, we use Infineon PSoC 6 wireless SoC. This SoC has many advantages for our smart toothbrush concept. First of all, it is utilized dual core ARM architecture. And we already mentioned that it's well suited for battery powered devices, the way it's energy efficient. Also, dual core architecture allows you to efficiently use various components of your system. For example, porting the ML model and all pre-processing algorithms to the Cortex-M0 and run inference there, thus leaving the Cortex-M4 for the Bluetooth stack, motor control of electrical toothbrush, and business logic. PSoC 6 has a newest Bluetooth core, 5.2, and support up to 2 Mbps data rate, which will allow you to collect the data for your dataset with a high frequency. It's always better to collect the data with high frequency because you can always downsample your dataset when you train your model. But to upsample your dataset is quite a tricky thing. But today we have a person who will tell you much better about all advantages of PSoC 6 than I am. Vivek Shankar from Infineon Technology. Vivek, please take a stage.
Thanks, everyone. Hey, everyone. This is Vivek Shankar Kannan. I take care of the PSoC 6 microcontroller product line. And as you have seen the demo and the accompanying data that was shown, right? Low power is important, and from that standpoint, PSoC 6 is a ideal low power edge compute platform. So with the dual core architecture, right, as Neuton's models, they could be deployed either on M4 or M0 plus, and we have both the cores available on PSoC 6, and it's built on a ultra low power 40 nanometer technology as well. So you have the flexibility to choose either of the core depending on your application needs, the M4 for the compute intensive tasks or the M0 plus for low bandwidth, low power processing. So typically the M0 plus we use for things like user interface, like capacitive touch processing, which kind of low bandwidth tasks, for example, whereas the M4 could be used for driving displays or running the networking stacks and ML algorithms. Having said that, the memory available is the same for both the cores. So you could partition the on-chip flash and RAM we have as per the application needs. There is no pre-configuration made. And also, depending on your runtime application needs, we have a dynamic voltage and frequency scaling option available. So you could switch between lower power frequency throttled operation or a higher, that's the ultra low power mode, or a higher frequency low power operation as well, even in the active mode. So that way you could, even in runtime active mode, you could throttle the power and frequency based on your application needs. And to support this multi-core application development, we also have the infrastructure available in our Modus Toolbox software. You have independent applications that could be developed for Cortex M4 and M0 Plus separately, and independent debugging of the two cores as well. And just to give a numerical color to the low power features I talked about for PSoC 6. So if you take the active mode, right, the M4, depending on whether you're operating in the highest frequency, what is called as the LP mode, it consumes 40 microampere per megahertz. But if you throttle down to the ULP mode, where the frequency is capped at 50 megahertz for the Cortex M4, it consumes only 22 microampere per megahertz. And even further reduction is possible if, for example, you go to the M0 plus operating domain. So naturally, compared to the M4, that's much smaller power profile. That's 20 microampere per megahertz and in LP mode, and 50 microampere per megahertz in ULP mode. And this ULP mode, again, the M0 plus can operate up to 25 megahertz, for example. But both these cores, if in the highest frequency mode, they can operate up to 150 megahertz M4 and 100 megahertz M0 plus respectively. So again, depending on the power modes, various peripherals are available. So you could, if the lowest power consumption mode, for example, is the hibernate mode, which consumes as little as 300 nanoamps here, all the peripherals are pretty much turned off, and you have very few peripherals like comparator, RTC, on GPU-based wake up available. The trade-off is obviously is that your wake up time is a little higher. But if you want a much faster wake up time, the deep sleep mode is another option. Here, the chip consumes 7 microamps, and you have a little bit more faster wake up time. And also the RAM could be retained as well, depending on your application. So there's up to 288 KB of SRAM in this part that's used for the demo. And you could configure how much RAM is retained between the low power mode in chunks of 32 KB, for example. So this gives an example of the low power features of the device. And obviously, for the kind of demo that was shown today, a single chip solution is preferred considering the form factor, and it needs to be low power at the same time secure with all the recent security trends on IoT products. So from that aspect, security is built into our platform. There is a ROM-based root of trust that ensures that only authenticated signed firmware images could be run, starting from the boot code that is immutable since that is in ROM, and if it has been tampered with by any mechanism, the integrity of that code is invalid, and further code execution would not happen, for example. And we offer the same dual core MCU platform as what is called as the PSoC 64 secured MCU variant, where Infineon makes the pre-configured security framework decision of using the M0 Plus as a SPE and the M4 as a NSPE, if you are familiar with the trusted firmware and terminologies. So that way you could use one domain for the secure processing and the other M4 domain for the non-secure processing, for example. Obviously, the standard security features like secure boot, provisioning, firmware updates are supported as well. And as I told, single chip solution is much preferred in these kind of small form factor products. From that standpoint, a lot of features could be integrated in the PSoC 6. So the housekeeping low power MCU thing could be offloaded to M0 Plus. And also the CapSense feature allows you to implement user interface capacitive touch sensing type solution in the same PSoC 6 instead of having a separate discrete touch processing IC, for example. So this, so if your wearable device has some portion of the product that needs to be activated on a user touch action, those kind of features could be implemented in PSoC 6 CapSense block, for example. And we also integrate some of the discrete logic gate functionality using what is called as the smart IO that's embedded into a GPIO fabric. That way, you could perform combinatorial operations like logic and or XOR within the device itself instead of using discrete chips outside. And this specific device includes not just the standard ADC comparators, it also has the DACs and op-amps built in. So any custom analog front end could be implemented using the same PSoC 6 instead of having to use external discrete analog ICs. So these are the integration advantages offered by this device. And even the kit that is used is a small form factor kit that was used by Neuton for this demo as well. Over to you, Blair.
Thank you, Vivek.
Raman, thanks.
Thank you. Yes, let's go to our practical tutorial. Unfortunately, we're a little bit out of time, and I will try to make it fast as possible. And first of all, I want to talk about the sensor data collection stage. And while you collect your sensor data for such applications, you should keep in mind two major, let's say, concepts. First of all, select the correct sensor sensitivity for data acquisition, as too low sensitivity will not able to detect small amplitude movements, and too high sensitivity will introduce a lot of noise and clipping into the data. For example, in this case, we was used the 2G sensitivity setting for Bosch BMI 116. And at the screen, you can see three different, let's say, settings for sensitivity. First of all, when the sensitivity is too low and the dynamic range is too high, for example, 16G or 24G, with such a high dynamic range, we cannot keep small details. And that's because it's not suitable for our project of smart toothbrush. And the second picture shows when the sensitivity is too high and the data is clipped. We cannot keep the certain patterns of our toothbrush session. And that's because it's also not suitable for feature extraction. And the third image shows when the sensitivity is chosen in an optimal way. We saw all details what we need. We saw that the data is not missed, the data is not clipped, everything great. The second concept is about the sampling frequency. And the sampling frequency is crucial for data analysis and feature extraction. If the frequency is too low, important details and variation of the data may be missed. But when you select the higher sampling frequency, it generates larger volumes of data. It requires more storage space. It requires more computational resources for analysis. And it can also introduce unwanted high frequency component into the signal. And for example, in this case of smart toothbrush, we collect the data with the 100 Hertz of sampling frequency. We use accelerometer and gyroscope sensor for data acquisition, 3 axes of accelerometer, 3 axes of gyroscope. And we will talk about the data processing stages in the next slide. For when you choose the right sampling frequency and right sensitivity, maybe also you will set up some digital filters for cleaning the data. You need to choose the right length of the window for analyzing your signal, as to not to lose important details, and so that the neural network understood the event according to the data from the window. And you see that if the window is too short, you did not keep the full event in your data session. If the data is too large, you can analyze the start of the second event or the unwanted noise in the window. So it's very important to choose the optimal window for such applications like a smart toothbrush or human activity recognition. And in our example, we use the data window of 1 second. So we collect 100 points of the data and do inference based on this data. And also it's worth to mention that to ensure a more continuous analysis of the signal, adjusted windows are often overlapped. And overlapping can help capture the transient and time varying characteristics of the signal more accurately. Okay, we will next talk about feature extraction. After you properly collect your data, you window it, you should extract the right features. And feature extraction is a crucial step in signal processing and analyzing. It involves transforming raw signal into the set of representative features that capture relevant information for further analysis or classification. And feature extraction techniques can be applied in the different domains, including the time domain, frequency domain, and time frequency domain. For example, if your data is pretty high frequency, you can use the frequency domain. You can analyze the FFT output. In our demo project, we use time domain features. And at the screen, you can see different examples of time domain, frequency domain features, for example, like skewness, kurtosis, zero crossing rate, or average magnitude difference. All right. Unfortunately, yeah, we're a little bit out of time, and I will skip the data collection part. You can collect the data if you have a device with various tools. There is a lot of open source tools that can collect the data. And I will start from the uploading data set to the Neuton platform, configure and train Neuton model at our platform, and we see how the ready trained ML package looks like. Okay. Let me share my screen. All right. I hope you can see my screen. And this is our Neuton AutoML platform. And here you can see all my projects. There is a lot of projects. You can create different projects for different devices, for different sessions, and etc. But let's start a new project. I call it Smart Toothbrush. All right. Now we should download your data set. I have already prepared data set of this smart toothbrush solution. And here it is. I just drag and drop it to our platform, and our platform will analyze the data in your data set, make it it should be sure that there is no missing data, there is no nonce in the data is clean and suitable for next processing. All right, the data is analyzed and we can use it. In our data set, we can explore our data set. As you can see, there is 3 axes of accelerometer and 3 axes of gyroscope, and the label. The current label of the activity, for example, is brush idle or front teeth. And we collect the data in the integer format. And this is a pretty interesting thing that in our platform, you can train your model. You can extract features in fixed mass format. You don't need to collect your data in a floating point because our neural network works perfectly with the integer-based format. And as you can see, the platform is automatically analyze your data, and it sees that your data type is in 16. That's right. We can select the task type for our smart toothbrush model. It's multi-class classification because we have several classes, and we can choose the metric that we will use for model training and optimization. And for this, we will use balanced accuracy because we're not sure how well balanced our data set. Next part will be about signal processing. And here we can choose the window size that we're talking about. For example, as I previously said, that our window size is 1 second. It means we sample the data in 100 Hertz frequency. So our data size, window size will be 100 points. And also we can use the sliding shift. And sliding shift, it means on what number of samples the window will be slide after the inference. For example, opposite value of data overlapping. For example, we can configure a different sliding shift for training. If your training data set is pretty small and you want to enrich, you have continuous session and you want to enrich your data set with a sliding window, you can do it. For example, I can make the sliding shift for training in 20 samples. And for inference, you can choose another shift because for example, you want to analyze your data not in 1 times per second, but 3 times per second, 5 times per second, then average your prediction and only then provide the prediction to your user. And we can use here 30 samples to make prediction each each 300 milliseconds. It means we have a prediction rate 3 times per second. And also, it means that 70% of window will be overlap. All right. Here you can select different types of features in time domain, in the frequency domain, etc. But I advise you to, if you're not an expert, stick with default one because our platform choosing the best one features for you. And that's pretty much it. You can only choose also the model type. And if you want to make your model as small as possible, you can use 8-bit bit depth of the model coefficient. So the model will be trained on the 8-bit weights and biases, and it will make your final solutions pretty small footprint, fast inference. It most crucial thing if your hardware does not have floating point unit. And that's pretty much it. That's simple and straightforward, and you can start training and see how it goes. Okay. All right, so I think we a little bit out of time. Let's go to the Q&A.
Thank you, Roman. Yes, we're going on 1 minute. So I'm going to ask as speedy as we can, Blair and Roman on your side, and Vivek, I'll try and bring you in. Speedy answers. Let's see how many we can get through. Reinhard, fantastic to have you joining, Reinhard. How long did it take you to collect and label the data for model development?
It depends on what stages you want to provide your model. For example, for proof of concept, you can have 5 people and collect the data session in about an hour. So it's 5 hours for 5 people. It will be enough for create great models that will be generalized more than, I don't know, 15, 100 people. But if we're talking about production grade model, for example, if your device has a great amount of cells and it's millions of users, of course, you should spend a little bit more time for data collection because it's more crucial part.
Thank you. And what did you use as a reference when training the model to know what location in the mouth it was in?
We use acceleration and gyroscope data. And with acceleration, you can determine the absolute orientation of the device. And based on the movement patterns and the orientation of the device, we can make the prediction of what area of oral cavity you're brushing.
Amazing. Thank you so much. And I'm afraid we are out of time. So thank you for those speedy responses. Sorry we didn't have enough time for more questions, audience, but we will endeavor to follow up afterwards. Blair, Roman, Vivek, thank you so much for a great presentation and an awesome, awesome demo. I always love when live demos are there. And it's even better that one actually, it all worked fine. There was the demo got shone on us today. It was really great to have that. So thank you all so much for great content. And thank you, audience, for your great questions. Sorry, we only had time to get to a couple. But do please join us in our next Tech Talk. We'll be hearing from Kern Concept on their fantastic hypervisor technology and how it's useful in the automotive space, and Sonatas the week after. And look forward to speaking to you and hearing from you soon. Please do direct any questions to myself. If there are any questions, recording will be live immediately after today's talk, as will the slides. And if you've got any questions for the Neuton folk, then please reach out to them or reach out to Infineon as well. Blair, Roman, Vivek, thank you so much for a great presentation today, and look forward to having you on again very soon. And audience, thanks again for your great questions and for attending today's talk. We'll see you soon.
Thank you, Tobias.
Thanks.
Thanks, everyone.